All right, so our objectives today is to learn about special products. So products mean the answer of special products of two binomials. They have specific names. You're going to have to learn them. One of them is called the difference of squares. This is going to come back up when we do factoring. The other guy is called a trinomial square. So we're going to learn about special products of two binomials. So this is only holds true of particular binomial times a binomial, okay? And the two types of problems that you explored last night on the homework. One answer is called the difference of squares. One answer is called a trinomial square. And then we're going to review multiplying polynomials. So on the second piece to your homework, you're going to actually practice multiplying larger than 2 by 2s. So I'm going to give you an example of what that's going to look like. Okay, so let's start with the first group of questions you did on the homework from the night before. This one had a very special situation. Now I'm going to just use variables. I'm not going to use numbers, just so that we can look at the general case. And then Flint, I'll have you pass these out when you have a moment. So the original problem would be two terms that are identical. The only difference between the two binomials is a sign change. Okay? So let's just list the criteria. Variables or terms match. In both binomials. So A matches A, B matches B. And there's different signs. Holy smokes. So we have one sum and we have one difference. Remember, sum is the answer to an addition problem. Difference is the answer to a subtraction problem. When you guys were doing this on your homework last night, when you distributed or did whatever technique, you multiplied A times A, you got A squared. You had A times negative B was negative AB. And then you had to switch gears and multiply B times A, and you got positive AB. And then you multiplied B times negative B, and you got negative B squared. And what happened is these always ended up disappearing. And you ended up with a binomial answer that had two squared numbers and a difference. That product is called the difference of squares. So if you recognize your original problem meets the criteria of terms match in both binomials, but there's a difference in signs, okay? I should say different signs. How about that? I just noticed that. Different signs. Then if you see that pattern and you understand it, then you know you're always going to get the difference of squares. And I can't remember who said it, but basically all you're doing is you're taking each of the terms and squaring them, and they're going to be separated by a minus. And the reason why is because the signs are always different. So again, if you are not understanding the pattern, you have other options that you don't need to memorize the pattern. But what you do need to memorize is that when you have an answer where it's a perfect square minus a perfect square, that's called the difference of squares. That's the key thing that you need to know, is that term the difference of squares, because again, that's going to pop up a lot. And it's very descriptive of what you have. You have the difference of squares. Now, just like what Connor brought up, is it may not always have a single a 1 as the exponent, and then when you square it, you get a 2 as an exponent. It could be any number that you square. So I'm going to give you an example to understand, so you have that in your notes. If your original problem is a cubed minus 3 times a cubed plus 3. So does it meet the criteria that both binomials have the same exact terms? Yeah, they both have an a cubed, they both have a 3. Does it meet the criteria that the signs are different? Yeah. So then we can use this shortcut, so to speak. And the shortcut says take each term and square it and separate them with a minus sign. So a cubed squared is a 3 times 2, right? So we get a to the 6 minus 3 squared is 9. Okay? So we can have different exponents. We could have multiple terms. We could have a monomial that has a coefficient and 3 variables with exponents on it, and we can square that using our techniques. And then it's going to say minus, and then it's going to be squaring whatever the second monomial is. Does that make sense? Okay, so the key to remember is that answer is called the difference of squares. Difference here, and this is a perfect square, and this is a perfect square. Okay, so that's why we call that the difference of squares. All right. So the next situation was giving you a problem that looked like this, where they started with a binomial only once, but they used an exponent. So the key was you had to understand that that actually stood for 2x minus 1 times 2x minus 1. So what we're calling this is we're squaring a binomial. So I'm going to write that down. We're squaring a binomial. So if I did my matrix and my FOIL, my columns, okay, Brian, you need to put that away. I'm going to multiply 2x times 2x, and I get, 2 times 2 is 4, x times x is x squared. I'm going to multiply 2x times negative 1 and get negative 2x. I multiply negative 1 times 2x, I get negative 2x. And I multiply negative 1 times negative 1, and I get positive 1. Looking for my like terms, I get 4x squared minus 4x plus 1. That answer is called a trinomial square. That's called a trinomial square. So we're always going to get a trinomial when we square a binomial, and that not only is a trinomial, but it's a very specific one that's called a trinomial square. So how do we get that? What makes it a square? That term is a perfect square. This term is a perfect square. Actually, let's do it this way. Another criteria, this must be positive because that indicates that you have multiplied the same sign by itself. Now look at 4x and look at your original binomial, 2x minus 1. So I have negative 4x and my original binomial was 2x minus 1. So how do you think I get 4x from 2x minus 1? What did we say when we were talking about this before? Patrick?
You multiply them.
Okay. Yep. I think you're on the track.
2, 5.
Say again?
I don't know.
Okay, what showed up twice when I did it the normal way? Negative 2x, right? It showed up twice, okay? where did negative 2x come from? 2x times negative 1. Where's 2x and negative 1 in your original binomial? It's the terms, right? So if I take these two terms and multiply them, I get negative 2x. But because my signs are exactly the same, when I do the other multiplication, I'm getting the same negative 2x. So basically, if you just take the terms in your original binomial, multiply them, double them, you get your middle term. So this is the product of the terms of two terms in the binomial. But the key is, since it shows up twice, we double it. Okay? So that middle term is the product of the two terms in the binomial, so the 2x and the negative 1, doubled. 2 times negative 1 is negative 2x, doubled is negative 4x. Okay? Last thing to look at is your sign originally in the binomial was a negative. The sign of that middle term matches, right? So I'm not always going to have pluses in this. It's dependent upon the sign in the original binomial. So this is the one that's the hardest for kids to see, but the key idea is you need to go back and remember, if you have anything that's in the format of a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared, which came from your a plus b quantity squared, or your a minus b quantity squared. These two answers are what we call trinomial squares. So again, if you don't see the pattern, you don't see the shortcut, no issues. You don't need to use it. All you need to do is be able to recognize an answer. Is it a trinomial square? Is it a difference of squares? Okay. Now, the problem is, when we get into factoring, you're going to have to recognize it, okay, because it's going to make your life a lot easier. So work on that now as being part of it. So you may, on your tests that you're going to take, not this coming Monday, but the Monday after that, you may be asked, is this a trinomial square? Yes or no? Just can you recognize it? Okay? All right, so we'll do want to do one more kind of problem. Let's do a polynomial times a polynomial, and I'm going to demonstrate how to do it all three ways, and then we'll go from there. So directions are going to say simplify. And let's do a binomial, x squared plus 4, times a trinomial, x squared plus 2x minus 3. So let's do distribution first. So with distribution, we take one term in the front polynomial and multiply by everything in the second one. So I'm going to multiply x squared times x squared, which gives me x to the fourth. I'm going to multiply x squared times 2x, which gives me 2x cubed. I'm going to multiply x squared times negative 3, which is negative 3x. I'm done multiplying by him, so now I'm going to multiply everything in the second polynomial by the positive 4. Positive 4 times x squared is positive 4x squared. Positive 4 times 2x is positive 8x. Positive 4 times negative 3 is negative 12. And then my job is to look for like terms. Come on.
For negative 3 times x squared, would it be negative 3x squared?
Oh, yes, you're right, sorry. This should be negative 3x squared. So now I'm looking for like terms, and I end up x to the fourth is the only one that shows up. I only have 1x cubed, so I get the plus 2x cubed. I do have 2x squared, so I'm going to add them together, and that gives me a positive x squared, negative 3 plus 4. And then I have an 8x, and I have a negative 12. Okay? So that's how I would do this with distribution. Let's do it with the matrix, or the box, area model. I'm going to call it matrix. So what I need to do is to first determine what my box is going to look like. So how many terms were in the first polynomial? How many were in the second? So what I have to do is create a 2 by 3 box to accommodate all those terms. Oops, that should be okay. And the way I create my box dictates where each of the polynomials go. So along the left side, I've got the x squared plus 4. In the numerator, I have x squared plus 2x minus 3. And then I figure out the area of each of the boxes. So x squared times x squared gives me x to the 4th. And the next one, I've got x squared times a positive 2x is a positive 2x cubed. And in the next box, I've got x squared times negative 3 is a negative 3x squared. And then in the next box, I've got 4 times x squared is, nope, sorry, too many things. 4 times x squared gives me a positive 4x squared. And then I have a 4 times a 2x gives me an 8x. And then I have a 4 times a negative 3 gives me a negative 12. So what's weird about this one is we need to look on a diagonal and see if we have any like terms. Do you see any like terms? Yeah, and they're not on a straight diagonal. And that's because if you notice in your polynomial, the first one, it went from an exponent of 2 to no exponent. So there's a gap in exponents. So when you look for your match, it's there, but you kind of have to stretch your view. Okay? So when we put everything together, in descending degree order, we have x to the 4th plus 2x cubed. Let's see, negative 3x squared and positive 4x squared is positive x squared. We have an 8x, and we have a minus 12. We get exactly the same answer we had before. The last technique is called column multiplication. And on this one, the key idea is to put your longer polynomial on top and your shorter one on the bottom. You're not lining up any like terms, you're just lining up last term with last term and going from there. So this is just a different way of showing your distribution. So we're going to multiply everything on top by positive 4. So positive 4 times negative 3 is negative 12. Positive 4 times 2x is positive 8x. Positive 4 times x squared is positive 4x squared. Now I'm going to multiply everything on top by x squared. X squared times negative 3, and this is where I line things up. So I get negative 3x squared. X squared times 2x is a positive 2x cubed. X squared times x squared is a positive x to the 4th. And we add it all up, and we get x to the 4th. Plus 2x cubed. We had one overlap with a positive x squared plus 8x minus 12. So the techniques we talked about can work with any size polynomial times any size polynomial. Notice how FOIL wouldn't work in this condition because FOIL has 4 letters and we've got more than 4 things that got to get multiplied. We have 6 things that need multiplying. So, okay? So that's what you're going to work on for the homework.